Okay, honors chemistry guys, I am so sorry these videos keep cutting off. So we have just finished potassium and calcium, and now we are going to start doing scandium. Now, if you notice scandium on the periodic table, we are actually in what we call the D block. So let's look at that on the hotel analogy. We have filled up the 4s, and notice the 3D block is what comes next in terms of energy level. So we actually start filling in not on the outermost ring, but back in the third energy level. Because remember, those d orbitals are kind of cloverleaf shape, so they take up even more energy than a 4s orbital, which is a simple spherical shape. So let's look at how we would do scandium. So when we look at scandium, we would have, I'm going to do the full one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we would have 3d1. Okay, so in terms of our noble gas notation, the noble gas in the period before scandium would be argon. So if we want to simplify this, we would have argon and we would have 4s2 and 3d1. So that would be our noble gas notation. So we're going to use the noble gas notation to do our orbital diagram just to simplify things. So we're going to do argon, 4s, both up and down, and then 3d. If you remember, when we have a d orbital, our L value is 2. So we can have our m sub L value be -2, -1, 0, +1, and +2. That gives us 5 orbitals. So we need 5 lines here for the 5 different orbitals. Okay, so we're just going to go from left to right as normal procedure, and we're going to fill in an upspin first. Okay, so that last electron that we put in is actually a 3D electron. Okay, so when we look at our quantum numbers, our n number is going to be 3. It is in a d electron or a d orbital, so our L number is going to be 2. The orbital we put it in was the very first one, so that is going to be the -2 orbital, and it is an upspin, so it is going to be a +1/2. Now, notice because this is the third energy level and not the fourth, our valence level, we only use the highest number in quantum numbers. We still only have 2 electrons here. So our valence, oops, I should put a C there, not another S. So let's erase that. So scandium really only has 2 valence electrons. Okay, so you probably feel like you know the drill here and how the pattern goes. I want you to go to Chrome and see if you can figure out that pattern. Okay, just pause the video and we'll check in just a minute. Okay, you guys ready? Okay, titanium. We're going to have argon. I'm going to do noble gas notation here. 4s2, 3d2. So our orbital diagram, argon, 4s, up and down, 3d, up and up. Okay, notice our last electron that we just put in right there is the third energy level. It is a d orbital, so our L value is 2. Our m sub L value is now -1 because we put it in the next orbital over, but it is still a +1/2 spin. We still only have 2 electrons in that highest energy level, so our dot picture for titanium is just going to have 2 dots. Okay, vanadium. Here we go. Vanadium. Argon. Oh, that is too thick. I don't want it that thick. Let's see if we can make it thinner. Okay, there we go. We're going to have argon. 4s2, 3d3. Okay, so argon, 4s, up and down. 3d, 1, 2, 3, 4, 5, up, up, up. So this will give our vanadium dot picture just 2 valence electrons. Okay, that last electron was in the 3rd energy level. It was a d orbital. It was the 0 orbital, and it was a positive 1/2. Okay, now chrome does a weird thing. So when we look at chrome, this is what it's going to do, and I'll show this to you. We would expect it to do this. We would expect it to do argon 4s2 and 3d4, but that's not what it does. So we would expect this 4s up and down and 3d 1, 2, 3, 4, 5, 1, 2, 3, 4. But that's not what it does. So I want to show you yet another rule here. These sub-levels are extremely stable when they are exactly full or exactly half full. So sub-levels are stable when exactly half full or full. So we're going to rearrange these a little bit. So here we go. Instead, this is how it's going to go. It's going to go argon, 4s1, and then 3d5. And let's show you what that looks like in terms of orbitals. So argon, 4s1, 3d, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Both of these orbitals, or these sublevels, I should say sublevels, both of these sublevels at this point get to be exactly half full, which is more stable than the arrangement that you would normally think. So chrome actually ends up having a valence electron shell of just 1 because there's only 1 electron in that 4s. So let me show you something. Let's get out the periodic table really quick. Where is my periodic table? Here it is. So let's open this up. So if I look at this, that means everything in the D4 column is going to do that. This whole column is going to have some configuration of 4s or S1 and then D5. Okay, so that whole column is going to do that. It's going to have something S1 and something minus 1, 5, D5. So let's write that better. X, S1, and then X minus 1, because it's 1 period behind D to the 5th. That whole column is going to do that. Okay, so let's continue on our pattern here. So we're going to go to, let's do our quantum numbers. Now, because we put that electron in the very last spot, because we move this one over, right? We are going to do, it's still a third energy level, it's still a d orbital, but it's now the +2 orbital, and it's a +1/2. Okay? So let's change color to do our next one. So manganese. We would expect manganese to be like this: argon, 4s2, and 3d5. And indeed it is. So this is what we would do. Argon, 4s, up and down, and 3d, up, up, up. 1, 2, 3, 4, 5, up, 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 up. Okay? So this one actually gets to be, we've got 2 valence electrons for manganese. So this will be 3, 2. We put this in the positive 1 spot. Okay? And then this is going to be +1/2. Okay, iron. So when we look at iron, we're going to add yet another electron. So we would expect this to be argon, 4s2, 3d6, and indeed that's what we get. So we get argon, 4s, up and down, 3d, 1, 2, 3, 4, 5, up, 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 and then down here. So once again, we only have 2 electrons in that highest n equals 4 level. So here we go. That electron we just put in, third energy level, it still is a d orbital. So, and we put it in the -2 orbital, but it's now a -1/2. Okay, cobalt, we're going to keep on adding things in here. So cobalt, we are going to do argon, 4s2, 3d7. So argon, 4s, up and down, 3d, we need 5 orbitals, 1, 2, 3, 4, 5, 6, and 7. Okay. Cobalt will have, whoa, what was that all about? Okay, cobalt will have 2 valence electrons. That last electron we just put in here will be third energy level. It's a d orbital. It's in the -1 orbital, and it's a -1/2. All right, so hopefully you're getting the pattern. Try the next couple. See if you can get it to work. Okay. All right. Let's see if you got it to work. Let's make this thinner. Okay, so nickel, 1 more electron. Argon, 4s2, 3d8. So argon, 4s, up and down, 3d, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, and 8. That will give us 2 valence electrons. That last electron we put in was in the third energy level. It was the d orbital. It was in this middle orbital, so that's the 0 orbital, and it was a negative spin. Okay? Now, copper does something weird once again. So let's remember this rule here. Things are extremely stable when they are exactly half full or exactly full. Okay, so let's look at copper. If we put in another electron, we can fill in this d orbital and we'll leave only one electron in the 4s orbital. So copper will fill in like this. Wow. My computer is once again having too much to think about. Let's try and erase that. It's not going to let me. Okay, let's close it. Let's try and figure this out. Oh boy. Okay, let's see if I can get this to work now. Okay, we were on copper. So let's go with copper. Okay, here we go, copper. So I said that copper was going to do something kind of strange, just like chrome did. So we will actually see this. We will see argon. We will see 4s1 and 3d10. This way, the 4s orbital is exactly half full, and the d sublevel is exactly full. This provides it more stability than if 4s was full and then the d orbitals weren't full. So we have half full and completely full, which is more stable. And that would be for copper. Sorry, I wrote that in the wrong spot. Copper. Argon. 4s1, 3d10. Okay, so ignore that. Let me put that in cobalt. So this is what it will come out like. 4s up and down, but we won't have the down in the s because that electron, actually let's map it out. Let's map it out really quick. We'll have 3d 1, 2, 3, 4, 5, 6, 7, 8, 9. That's how you would normally write it. But this electron right here jumps up here. So we end up having it looking kind of like this. We end up having 4s1, 3d10, which gives copper just one valence electron. That last electron we just put in was in the 3d, so L is 2. We put it in that last orbital. Well, actually, let's just write it in this one. We wrote it in the positive 1 orbital, but it was a negative down spin. Okay, so zinc. Let's put in zinc. Let's choose a different color. We'll have argon, 4s2, 3d10. So 4s up and down, 3d, 3, 4, 5, up, down, up, down, up, down, up, down, and up, down, which will give zinc 2 valence electrons. That last electron that we put in, it was in the 3rd energy level. It was a d orbital. It was in the positive 2 orbital, and it was a negative 1/2 spin. Okay, gallium. So if I look at gallium, I have, let's get my periodic table up here again. So if I look at gallium, I'm now back into the P block. So I'm back into the P block. So if I look at my periodic table and I look at the hotel analogy, let's see if I can find my hotel analogy really quick. No, it's still thinking. So if you look at the hotel analogy, we are going back to the P block. So we would expect us to have argon 4s2, 3d10, and then 4p1. So we will have 4s up and down, 3d, 1, 2, 3, 4, 5, up, down, up, down, up, down, up, down, up, down. And then 4p, we will have 3 orbitals here and this. So that last electron, we now have 3 electrons in the 4th energy level for gallium. So we would expect a dot picture like that. That last electron we put in the 4th energy level, it was at p orbital, so our L value is 1. We put it in the negative 1 orbital, and it was a positive spin. Okay, germanium. So let's change the color again. Germanium, argon, 4s2, 3d10, 4p2, 4s, up and down, 3d, up, down, up, down, up, down, up, down, up, down, and then 4p, up and up. So for germanium, we would expect to have four valence electrons. So our valence electron dot picture will look like that. That last electron we put in was in the fourth energy level. It was a p orbital. It was our middle orbital. So it was a 0 orbital, and it was a positive spin. Okay, next one, we have arsenic. So we're going to have argon, 4s2, 3d10, 4p3, 4s, up and down, 3d, that's all going to be full, and 4p, up and up. So you'll see for arsenic, we will have 5 valence electrons. So we will have 2, and then 1, 1, and 1, showing the distribution through those orbitals. It was a fourth level. It was a p orbital. It was in the positive 1 orbital, and it was a positive 1/2. Okay, selenium. We are going to change our color again. So for selenium, we will have argon, 4s2, 3d10, 4p4, 4s, up and down, 3d, that will be totally full, and 4p, 1, 2, 3, 4. Okay, so for selenium, we would expect a dot picture like this. 1, 2, 3, 4, 5, and 6. So that will give us 1, 2, 3, 4, 5, 6 valence electrons. Okay, that last electron we put in there, fourth level, p level. We put it in the -1 orbital, and it was a negative spin. Okay, bromine. Let's change our color once again. Bromine, we're going to look at argon, 4s2, 3d10, 4p5. So this will give us 4s, both up and down, 3d, 1, 2, 3, 4, 5. All of those orbitals will be full. And then 4p, 1, 2, 3, 4, 5. So that will give bromine, that will give bromine 7 valence electrons. One, 2, 3, 4, 5, 6, and 7. That last electron we put in, fourth energy level, p orbital, it was the middle orbital, so 0, and it was a negative spin. Okay, and then last but not least of our things, krypton. Argon, 4s2, 3d10, 4p6. So 4s, up, down, 3d, 1, 2, 3, 4, 5. This is totally full. And then the 4p will also be totally full. So krypton will have 8 valence electrons around it. Have you noticed a pattern as we go across the periodic table with the valence electrons? we'll put these patterns together on the next video. So our quantum numbers, 4 for the fourth energy level, 1 for the p orbital, positive 1 for this last orbital that we put it in, and a negative 1/2 for the spin. Okay, so that is how we do orbital notation, how we do electron configuration, and quantum numbers with the periodic table. We're starting to put the patterns together next class period. Hope you had a great day. See ya. Bye.